Well, today I would like to talk about this research project which has been going on over the past 6-7 years at UNSW Sydney, and give you an overview of steel timber composite system as an alternative to conventional steel concrete composite floors. The project, as I said, started in 2015, around 2015. After that, we got some funding from the government and it took off from there. And what I'm going to present today is basically the result of this research project. Pretty much most of the structural engineers are familiar with steel concrete composite floors. Basically, we have a reinforced concrete slab connected to steel beams by means of some shear connectors. And then in this composite cross sections, reinforced concrete slab is basically responsible for taking the compressive stresses, and all the tension, or a big part of it, is carried by steel bars. Based on this simple concept, we came up with this idea, which is steel timber composite, meaning that we replace the conventional reinforced concrete slab with timber, specifically cross-laminated timber, or CLT, and laminated veneer lumbers, LVL, to see how we can develop a steel timber composite system, which is lightweight, of course, more sustainable than conventional steel concrete composite floors. To connect these two completely different materials, I'm saying timber, let's say, and steel, we used mechanical connectors, something which have been used for many centuries in let's say, construction of timber structures. And of course, the modern type are high strength bolts and lag screws made of, let's say, high strength steel, etc. On the left, you can see a variety of mechanical shear connectors we use to connect timber to steel to develop this steel timber composite system. Initially, we did some assessment of the advantages or benefit of this steel composite system compared to other methods, conventional methods of constructions, more specifically reinforced concrete and steel concrete composite. So in this slide, you can see a list of different advantages, such as speed of construction, of course, sustainability, the possibility for recycling of the material, lower self-weight, and of course, that lower self-weight will lead to let's say, a less need for craneage or propping, etc., during the constructions. And also the reduction in the self-weight would be assisting us to reduce the size of beams, columns, and footings, typically made of steel and reinforced concrete, which both of them are very energy and carbon intensive materials. Apart from that, the cost of substrate foundation, in particular, if you are building something in a soft problematic soil or a construction site, would be also another benefit of this system. And the last one is basically upgrading or drop-top solutions, or adding stories on top of existing buildings, which are becoming more popular and common, as you might have noticed, in especially densely populated urban areas, would be another advantage we can get out of this steel timber composite system. We did some analysis in terms of what would be the sustainability achievement we get out of the steel timber compared to conventional system. 5-story, 10-story, 15-story buildings, some hypothetical buildings were considered. We designed them as a reinforced concrete, as a steel concrete composite, and as a steel timber, and did some, let's say, life cycle analysis to see what's, let's say, the carbon footprint or the amount of CO2 per, let's say, in kilogram emitted per square meter of each one of these buildings. You can see a range of results on this end of the spectrum. You can see the reinforced concrete one, this RC 5 to 15 referring to reinforced concrete. SCC refers to a steel concrete composite, 5, 10, 15 story. And then on the right side of this graph, we have like steel timber composite floors, which obviously have lower, let's say, embodied carbon in per square meter of the buildings. If we consider, in fact, the sequestration of the carbon in timber, then we would end up, in fact, with some negative values, meaning that that building can act as a carbon storage. and that's what we can achieve out of this system. Also, we did some cost analysis in terms of how the cost of steel timber composite for conventional buildings like 8 to 9 meters span, 6 to 8 stories tall, would stack up against conventional steel concrete composite system. And roughly the cost is around, let's say, 20 to 30% higher considering everything. And I'm just talking about the cost of structures. Now, let's just go back to what I earlier indicated, that research project about steel timber composite system and its advantages, and what we did, in fact, to demonstrate the feasibility of this steel timber composite system. The research project had 3 main components, including an experimental program, stage 1. Stage 2 involved developing some numerical models for efficient and accurate, let's say, finite element or analysis of this steel timber composite system. And stage 3 was developing some simplified design provisions that can be used for day-to-day design of such steel timber composite system. On the short-term test, we had push-out 4-point bending, what we call push down. On the long-term test, we have material testing, including, let's say, establishing the mechanical properties of material, such as elastic modulus, compressive strengths, bending strengths, tensile strengths, as well as moisture content and coefficient of diffusion, which we needed for long-term analysis of any kind of timber structures or hybrid timber composite structures. Apart from that, we did some long-term push-out tests under sustained load. We kept the load constant to see what happens to the connections. We did the same thing on steel timber composite beams, 6-meter long beams, close to a full-scale beams. We tested them under constant load. We measured the deflection to see how these steel timber composite in terms of the stiffness and in terms of the deflections, which are of importance from serviceability design point of view, would change over time under a variable environment, variable relative humidity, and variable temperature. Also, we did some analysis on the vibration behavior of these steel timber composite systems to see whether we can satisfy the existing design requirements for conventional, let's say, residential buildings and offices when it comes to human-induced vibration design requirements. Now, in the next 10 minutes or so, I will take you through each one of these tests that we did, also try to highlight the importance of each one of these tests and why we did it and what the outcomes are and how we can use these results, in fact, for, let's say, practical analysis and design of steel timber composite systems. The first one is what we call the push-out test. So we have a steel profile at the middle, then it's connected to 2 CLT panels on the side. The connection, as I indicated earlier, could be conventional mechanical fasteners like bolt screws or something else. What that something else is, again, I can show you an example of other alternatives for a shear connection between timber and between steel in the next few minutes. And then we apply a load, we push this down, and then we measure the load versus relative displacement of these 2 components, timber versus steel, and that's the type of results we get, what we call load versus slip. And this would basically shed some light on the performance of the connections, which have critical role in design of any composite floors, including steel timber composite floors. Of course, we are interested in stiffness, we are interested in strength, and also ductility of these connections are important, especially under extreme loading conditions, when the shear connections are pushed to their limit and beyond. Just a simple comparison between 2 types of connections, let's say screws versus bolts. You can see clearly from these load slip diagrams. Screws are obviously more ductile. You see there is no sudden drop in the load after the peak, whereas bolts, they exhibit quite brittle behavior associated with sudden shear failure in the bolt and the load suddenly drop. So in terms of ductility, definitely screws are performing better than bolts. In terms of strengths, it's completely opposite. Bolts have higher strengths than conventional screws, and the screws I'm talking about, these are conventional coach screws that you can get off the shelf with and manufactured from, let's say, mild steel, 4-6 steel with yield strengths of around 240. And in terms of stiffness, again, screws initially have higher stiffness, but bolts have a slightly higher stiffness after the first initial slip, let's say. If the bolts could be tightened to mobilize friction, definitely the initial slip would be much smaller. Again, we did some bending tests, as I said, some 4-point bending tests to see how the results are stack up when we look at, let's say, the load versus midspan deflection. So this is a bare steel beam, the dot line, and the solid line is a steel timber composite beam. So you can see there is a 50% strength enhancement when we are using coach screws 16 millimeter, 250 millimeter apart, which is quite reasonable. In terms of stiffness, again, the initial stiffness of this composite system is around 60-70% higher than the bare steel beam. This is another type of connection. As I said, one critical factor in design of steel timber composite floor is the stiffness of the shear connectors and the serviceability design requirements related to long-term and short-term deflections. So the stiffer the connection, the better definitely the performance of these steel concrete composite floors would be. Unfortunately, bolts and screws are not really the best performer when it comes to the shear connection between timber and steel. The idea we had is to replace conventional shear connectors with something which is easier to be installed, considering all the constraint in the construction side. It could be installed from the top rather than bottom, which makes it, again, very difficult in real construction side. And we came up with this idea. So we cut a hole like a square one, and then we installed the stud or bolted shear connectors on top of the flange. We fill these pockets with cementitious grout, and we got very good connections with very good stiffness, as you can see from the initial slope of these graphs, very high strength, as well as very good ductility. So we got a fairly good connection in terms of stiffness, strength, and ductility, as I said, which all three factors are important from structural design point of view. Again, we tested a variety of different connections to see how far we can push this system to the limit. And of course, the limit, when I said when we have a near full composite action, and that could be only achieved by gluing or using adhesives. And when we glued the CLT slab to steel beams and also use some let's say coach screws to achieve some level of ductility, the highest strength enhancement we got was close to 90%. It means that a bare steel strength could be doubled by developing composite action. And we are talking about CLT slab, which are like 100, 120 millimeter thick, and steel beams, which are 310 UB or around the same size. So you can, from there, imagine how much strength and stiffness enhancement we can achieve. The next part was to compare steel concrete and steel timber to see, okay, whether steel timber is really performing on par with steel concrete. That's what we tested. Again, an 800 millimeter wide slab. Once we have a reinforced concrete, and then second time we had a CLT slab connected to this 310 UB32, and we did the load deflection. We just tested these beams, and these are the results. The red one is basically steel timber, and the blue one is steel concrete. You see, in terms of ultimate strength, there is not much difference. In terms of ductility, in fact, steel timber, interestingly, is more ductile than steel concrete. In terms of stiffness, of course, due to lower elastic modulus of timber compared to concrete, steel timber composite has a slightly lower stiffness. And when saying slightly, it's around 50-60%, but still, it's definitely much higher than a bare steel beam. Apart from the short-term test, as I said, we did some long-term tests to see how the deflections basically increase over time under sustained load. You see on the back, we have sustained push-out test. In the front, we have sustained load bending tests. These are like 6-point bending tests. And you see the mechanism with device for applying and keeping the load constant. These specimens, 6 meter long, were under loads for nearly 2 years. We measured the relative humidity in the lab environment, temperature, and from there we measured the midspan deflections, let's say end the sleep, a variety of different parameters measured during the test, and those test data were used to evaluate the long-term performance. The one, in fact, simple graph we get out of this long-term deflection is something like this. We have midspan deflection, which has been expressed as a percentage of initial deflection versus the time. You can see over time the deflections increase, and these jumps or drops or are associated with, like rainy days or dry days when we have this hygromechanical behavior of timber kicks in and affect basically the deflection measurement we have. Well, to summarize the outcome of long-term deflection after 22 months, the creep coefficient we measured for the 6 beams with a variety of different connections was somewhere between 0.15 to 0.3. And when we extrapolated the results by fitting some, let's say, log normal models and doing some computer simulations, the long-term creep coefficient was around 0.25 to 4. Let's say if we use 0.5, it would be more or less something that can take care of long-term deflection, meaning that your initial deflections multiplied by 1.5, it gives you a value of, multiplied by short-term deflection, it gives you the value of long-term deflection. If we look at the beam to column connection behavior, because one of the interesting aspects when we have the composite system is to see how continuity of the slab would assist us in developing Hawking bending moments, increasing the let's say, stiffness at beam to column connection, and accordingly reduce the midspan deflections, which again assist us in satisfying the serviceability design requirements. Also, this bending moments provided at the beam to column connection zone can be relied on as part of the lateral load resisting system, like a moment resisting frame. We did what we call a push-down test. You can see what a push-down test look like. We have a column at the middle, and then we push down these ends of the beam, which we call it a subassembly of the beam to column connections. And then we can measure the load, we can measure the rotation, we can measure a variety of different parameters. And from there, we can evaluate the structural performance of beam to column connections. We look at flush end plate, we look at like, let's say, shear tabs, web cleats, a variety of different beam to column connections, and that's the setup we use. Typically, we flip over the whole specimen, we apply the load at the middle, and then we have reactions upward, which creates the same effect as doing the direct push down test. And again, in terms of CLT to CLT connections, we try to use some of the connections typically used in industry for mass timber floors, like SP-line joints with LVL panels, like half-lap joints using bolted steel plates, and these type of connections which are easy to be implemented and constructed. These are some of the failure modes you can see, like plug shear, block shear down the bottom on the right. You can see tensile failure, rolling shear failure in the lamellas loaded perpendicular to grain. Again, rolling shear, tensile failure, and a variety of, again, failure happens in CLT slabs. Again, we came up with, again, some other alternatives for connecting the CLT to CLT at this location, where the two panels meet each other at the column joints. And we use this method, which is like basically embedded threaded rods, and we got very good result out of it. And you can see, again, we use these shear pockets, we fill them with, let's say, cementitious grout to protect the bolts or mechanical shear connectors from exposure to whatever outside is, including possible fire, etc. Again, the results we get out of the push-down test is load versus midspan deflections. I just want to highlight a few things on this graph. You can see a variety of different connections. You see the glue CLT plus, like, let's say, steel plates. We got this graph, which goes all the way up, and it shows a peak load close to 400 kilonewton. Just keep that 400 kilonewton number in mind, and then you will see in the next slides, then we test like steel concrete composite floors with continuous reinforced concrete slab. We got strengths close to 440, which is just 40 kilonewton, or around 10% less than what we get from steel concrete in this case of steel timber composite floors. Again, we tested bare steel beams, and we compared the results. One thing is the brittle failure when we have glued use for connecting the CLT panels, which is not ideal, and then the load drops and follows pretty much bare steel beam to column connection behavior. Look at the case where we have a steel concrete composite. You see this RCS slab here, up here, that solid line is basically around 400 2430 kilonewton, which I said is just around 10% more than what we had in the steel timber composite beam to column connections with, let's say, 2 plates top and bottom on the CLTS slab. Again, the same graphs, more or less, the results consistently demonstrate that out of this CLTS slab, we could get quite a lot of stiffness as well as strength provided at the beam to column connection zone. And of course, if we can rely on this and take it into account in our design, that would assist us to reduce the size of beams to some extent, and also enhance the lateral load resisting system in terms of stiffness as well as strength against, let's say, wind, seismic action, etc., when needed. And these are the results related to that connection with embedded steel bars. Just to conclude, well, steel timber composite or steel CLT composite is a viable alternative to conventional steel concrete. Gluing is ideal. It provides very high stiffness and strength, but definitely it's not really ductile. And that's the big downside when we want to use glue in this kind of connections. All the other, again, conclusion, the other two are more or less demonstrating that steel timber composite beam to column connections can be basically relied on as part of the lateral load resisting system, and the strength and stiffness provided can be used to have a more efficient design in practice. The next part of our project, which I very briefly just try to provide for you some background and then go through it, is about modeling. Whenever we do any test, okay, we do a limited number of tests because testing is very expensive, costly, time consuming. Immediately after that, we try to build models. And when I say about models, these are the models that we can use as a predictive tool, as a tool that we can predict the behavior and generate more data that are really reliable. And it's not just a data fitting exercise. That's what we are interested in when it comes to modeling. And of course, that model should capture the failure mode, should capture stiffness, strength, as well as peak and post-peak behavior of the let's say steel timber composite system or any kind of composite timber floors. And apart from that, from those models, we could get good load deflection diagrams, reasonably accurate one when I said good, or moment rotation diagrams. One of the challenge always in this kind of modelings we need to keep in mind is the contact and interaction between different components, especially the effect of friction, which should be taken into account if you want to have a good model. We develop a model. That model involved quite some level of, let's say, derivation and rigorous mathematical, let's say, implementation of the model in a computer code, in Abaqus specifically. In this case, we recognize, let's say, an anisotropic behavior of timber in different directions, and we try to implement that. This is typical, let's say, uniaxial material behavior we plug into our model. So we implemented this piecewise linear model to ensure that the results basically could be adjusted when needed, or let's say we can use it to fit it into different kind of behavior, tension, compression, whatever is needed. So to do the modeling of timber and steel timber specifically, we need elastic modulus in 3 directions, we need Poisson ratio, we need shear modulus. And apart from that, we need compressive strengths, tensile strengths in different directions, parallel to grain, perpendicular to grain. We need shear strengths, we need rolling shear strengths. One parameter which we always have a challenge to basically establish is the fracture energy. Recently, there has been quite a few theses coming out, mostly done in Europe, in Austria, and in Sweden. They try to basically measure the fracture energy, which provides for us a very good benchmark when we want to do this kind of modeling. We did a variety of modeling. Just one thing I would like to highlight towards the end of my presentation is the importance of modeling and what's really, what challenges, in fact, we have when we want to do this kind of modeling exercise. We started very simple by modeling a dug bone sample. we applied some uniaxial tension, and we got the results load versus displacement. One thing you would notice from here is when we use a coarse finite element mesh, we got this graph. When you use a fine finite element mesh, we got this graph. So obviously there is some mesh sensitivity here. And it's not just specifically this particular example or this particular type of sample. Any kind of timber structures subjected to tension, to combination of tension and shear, more or less you should expect the same thing. So we try to resolve this by basically coming up with what we call a localization limiter. It means that it prevents the model to have the cracks localized in narrow band. And that's in fact the reason for that sensitivity you see. We tried again to do further modeling in terms of modeling, let's say, the load sleeps and capturing the load sleeps of STC connections like this one under pushout. So this is the type of model we did. One thing again I want to highlight is the importance of the contact and how you have to model this. A very good reference to that would be a thesis done in Vienna Institute of Technology by Michael Dorn. And he has done extensive work on different interfaces between mechanical connections and timber. And you can use as a reference to basically introduce a proper contact at these interfaces and get good results without tweaking or fiddling around with your model, and use it for predicting the results. This is one example. So you see the finite element model prediction on the right, the extent of the damage versus the test data, extent of the damage on the left. Again, these are the type of deflections you see or deformation you see in the screws, very similar in terms of the number of plastic hinges, quite consistent with the test. In terms of load versus sleep, again, you see there are quite consistencies. And you see the Eurocode predictions completely, of course, is conservative when we apply it for this steel timbered composite connections. The next stage was basically modeling the beam to column connections. Like what I said, again, whatever test we do, immediately after that, we use this modeling exercise to basically expand the library of our test data rather than expending a hefty amount of our funding on just testing. We do this exercise and we validate them against the test data. And again, from there, we use them for further assessment or evaluation of any system, including the steel timber composite system. This is another example. You see the beam to column connections. We just consider the symmetry of the structure to reduce the size of the model and make it more efficient from a computational point of view. And we analyze the model. Again, I just want to highlight the importance of the mesh sensitivity. You need to keep an eye on this. You see on the left, we have used an ordinary model available in Abaqus. In fact, you see the extent of the damage. And then when we implemented that localization limiter or non-local model, you see the extent of the damage and the damage propagation, as well as the extent of the damage which appears as rolling shear on the lamella loaded perpendicular to grain. This one on the right was quite consistent, as you can see down the bottom with the test. You see tension here at the outermost lamella, as well as rolling shear in the layer or in the lamella immediately to that one. And the same happens, in fact, in the model, whereas conventional models are not really capable of capturing these aspects. Likewise, when we look at the load displacement, you see the peak load from basically the experiments. The dashed red line is 159. If we use that model with non-local model with localization limiter, we get a peak load of 151. If you use a local model, you get 127 kilonewton. And you see there is a difference. And again, these are what we really care about or pay attention to, because we need to make our predictions as precise as possible. Otherwise, of course, we can't really fully exploit all the advantages of any innovative structural system, including these ones. In the very last slide, I would like to highlight again in the second part of my presentation, the importance of the mesh sensitivity. If you're doing this kind of modeling exercise, always remember, you need to do definitely a reliable mesh sensitivity analysis to demonstrate the robustness of the results. And if the results are not robust, definitely you need to use localization limiters to get the good prediction and reliable predictions. I would like to again acknowledge the funding we received from Australian Research Council to conduct this research, as well as the contribution from my colleague, Professor Mark Bradford, in this research project. Thank you so much for your attention. And this was my last slide, so I just pass it to Wendy to basically go through the next part of the presentation.
Thank you very much, Hamid. It's great to see the great amount of detail that goes into the research. At this stage, I would like to pass it over to Nick. Thank you very much, Nick.
Thank you, Wendy and Wood Solutions. Just want to check that everyone can see my screen.
Yes, we can.
Great. Awesome. Look, I wanted to talk today about mass timber concrete composites, or basically, why concrete doesn't have to be the enemy. There seems to be certainly a feeling, I think, in industry that concrete's somehow the big bad enemy of timber. I want to show you today why they can work together. But everyone's here today because we all love timber. That's why we log on to Wood Solutions webinars. We're all converts. We all know very well the benefits of it. I've worked in the industry for a number of years now, and advantages such as lightweight material, the sustainability, the aesthetics, the speed of install, are called up time and time again as benefits of timber construction. But sitting on the other side of the fence, there are also a lot of drawbacks to timber or challenges. Combustibility being one of the most commonly raised ones. Acoustic performance, with timber being relatively lightweight. The ability to generate large diaphragm actions within the structure, or the lightweight nature of the floor kind of working against timber, working against sort of high dynamic performance. So what might we do to combat these? So, we look at classic combinations, fish and chips, Batman and Robin, or if you're American, peanut butter and jelly, though I never got that one. So why can't we use timber and concrete together more? So looking back at my list of why not to use timber, those four kind of top reasons that are kind of brought up time and again by people, looking to kind of better understand the system. When we look at concrete, it pretty well combats all of those. So it's definitely non-combustible. It's much more heavyweight construction than timber, so it performs a lot better acoustically. It has an easy, natural kind of diaphragm action through the slab, and it being heavyweight can also help to dampen vibration. So, bringing those two materials together, we can generate a composite material that can perform much better than the sum of its parts. So timber concrete composites, or TCC floors. Hamid's already been through this in a lot of detail, so I'm not going to dwell on this now, but in a basic sense, concrete works really well in compression, timber works well in tension, and will effectively replace the tension steel in a traditional slab. The key consideration for all these systems is how do you join the two together? So the better the connection between those, the more effective the floor system is. And Hamid's kind of presentation showed some different options and things for those. So that's really the key design parameter when you're considering TCC floors. So my own journey into TCC floors started one of the earlier projects I worked on in Australia, the Melbourne University Faculty of Architecture. Pretty sure that won the Timber Design Awards back in the day, but what people don't realise is that there was originally proposed to be a TCC floor over all the upper levels. So you see the image on the right with a CLT soffit, and there was a large concrete topping that went over the whole system. That was largely driven by some of the enormous diaphragm forces that were generated within the building with the atriums and some large cantilever sections of building. we needed the concrete, so and we needed it for acoustics. So why not combine the both materials and get a better performing system? Sadly, the builder replaced it with Bondec and plasterboard, which was very much the kind of what was happening at the time in the industry. But what we did do as part of that, and as part of the university's design, was we trialed a number of different connection systems and did some full scale tests. So looking at the kind of CLT concrete composite, the methods that we trialed were so glued in mesh plates, routing notches into the CLT, or inclined screws. Both the mesh plates and the screws are proprietary, whereas the notches was based on kind of design guidance available. And we tested them all, and they performed exceptionally well. The screws and plates had very, very high ductility, significant reserve strength after the failure of the composite connection. The notch test had an astonishing amount of strength and performance, but slightly less ductile failure, which is something that we would propose to improve through further testing if the floor had gone ahead. But all of them significantly exceeded the service design capacity of the floor. So this was my first experience of TCC floors, and I think what was clear to me was that they actually worked incredibly well, and they really harnessed the benefit and performance of both materials. So when it comes to designing them, I think there's probably a lot more information out there than people realize. I don't know if there's a virtual show of hands from just how many people knew that Wood Solutions Design Guide 30 is actually based all around timber concrete composite floors. So it's based on the old Xpan research from several years ago, where a set of universities and research institutions from across Australia and New Zealand got together and did some research around timber structures, and TCC floors is one of them. So for anyone any structural engineers in particular that are looking for design guidance and calculations and nice graphs and stress plots, I highly recommend you download this and take a look, because it really walks you through the fundamentals very, very carefully. This guy with his large tool is very happily selling the SFS inclined screws. So these are like, they're functional like shear studs in a conventional steel concrete composite floor. So they have a kind of collar on them, and the head sticks out into the concrete. So when you cast the concrete on top, they form a shear bond between the timber elements and the concrete. So there's a range of proprietary guidance that's available from SFS on these. What we found was the inclined screws give far greater performance than the vertical screws. Just the better alignment of the forces and actions that are present across that joint. And you'll notice as well from here that typically in Europe, a lot of these floors are based around kind of joisted floors. So a glulam beam, either ply or a thin CLT plank to act as formwork, and then the concrete over the top. And that's probably some of the best bang for your buck in terms of material to performance. The other option as well, is similar to the one we tested at Melbourne Uni, was the HPV plates. So these could either be done on site or in the factory. They are slightly flexible and flimsy, so you'd need to, if you were to do them off site, you'd need to look after them kind of carefully and make sure your Rio is up on bar chairs or something to stop them getting crushed. But again, these work very well, and there's plenty of proprietary design guidance on these. Another one that I've not seen used before is a system by Worth, who are a big German screw manufacturer, which is a kind of post-installed or pre or post-installed screw system. So some of the images you'll see here of this shear key being put down on the floor on the right-hand side prior to casting a slab. On the left-hand side, they're actually craning in precast planks and fixing these post. So there's potential to use these in an entirely dry floor system if that was something that was a benefit for the particular project. Quick word on fire performance. The two kind of methodologies that are proposed for designing these, one would be to ensure you've got sufficient char zone that doesn't interact with the fixings. Need to kind of recheck the composite behavior and stresses across that section with the reduced properties, but be able to sort of demonstrate compliance through that. The second option, which may be simpler but may not be as cost effective, would be to completely ignore the contribution of the timber and the fire and design the slab for slab reinforcement for the fire condition only. So that might be an easier one from a compliance point of view, given that you could do that as essentially deemed to satisfy. But that's something we need to work through on a project by project basis. Now time for me to shield some product. This is the strong floor system that we've worked on for the last 12 months. This was born out of a conversation with various kind of parties who were looking at a mass timber building, but wanted a concrete finish. So, why not combine the best of both? So this is a floor system that we've developed. It's effectively like a king floor or a bond deck slab with an integrated glulam soffit on the bottom. So combining the benefits of all those systems, but as a piece of kind of permanent formwork, the system can span up to 9 meters. So there's two different options, whether depending on the channel height, and the deeper one, the 375 overall floor thickness, can span 9 meters unpropped in the construction case. Cast the concrete and end up with a very high performing floor system. So we've been working with various partners at the moment, and we're just about to start manufacture on the first project this week. So it's proving to be a really kind of high performing system. We've been working together with Delta Beam, which is a permanent sort of steel formwork. So it's available from a company called Becco. Highly recommend you check them out. The product itself is a kind of a hollow trapezoidal steel beam with the idea that the strong floor sits on the bottom flange, and then the whole thing's all cast in together. So looking at the picture before, you end up with a much more open soffit. You don't end up with all the beams to try and coordinate with or penetrate surfaces through, which can save a lot of cost. Could save height off the building as well. So we're certainly seeing some interest in projects using these systems together. So we've been working through structural testing on both channel systems. We're 6 months into a long-term test of the floor, looking at creep performance, with the results significantly exceeding expectations. So we've tested lifting and fall arrest. We've tested construction conditions. We've tested in-service conditions. So the floor system, like I said, is going into its first project imminently, and we're working already on the design of the next few to come. So the fire compliance aspect of it has been another area we've concentrated on. We've done a lot of testing on the panels itself, as well with services penetrations through, and we can achieve up to a 120-minute FRL with this system. For those who follow me on LinkedIn, you see that we recently completed some acoustic testing as well a week or two ago. Again, excellent performance of the floor system. So one of the relative Achilles heels of timber floors is their lightweight nature, and acoustic performance is very strongly related to weight and density. So particularly at low frequency sound, the timber struggles. So we have to add additional materials to your average CLT floor, whether that's screed, whether that's putting FC sheet on or putting in access floors. These are all relatively expensive, but TCC floor can pretty well achieve compliance solutions for residential and commercial buildings without significant build-ups on top. So just a few examples. I realise we're getting kind of close to the end of the hour, so I'll try to speed through these. So these are some examples from around the world. The Lifecycle 1 tower in Germany, precast concrete and glulam beams for the floor solution on that. The University of British Columbia Earth Sciences building. This one was all cast in situ. Again, so seeing a lot of use over in North America and Europe. TCC floors seem to be a lot more accepted over there. I think due to kind of requirements around acoustics and vibration being a little bit more stringent on the continent. They seem to be a kind of larger part of the market over there. There are some examples around in Australia, and I picked this one because it's one of my favourites, which is a beautiful building that it's in Melbourne, the RMIT Garden Building, Vic ash and beams and columns and a composite concrete slab over the top. And for those who are sort of following some of the arms race in tall timber, I think there's more and more kind of consideration of hybrids, hybrid materials, hybrid structures and systems. So this is the SOM version of timber concrete composite floor with composite slabs and then reinforced beam sections as well. So they recently tested these for over a 2-hour fire test on a full scale floor. I think that we're going to see more and more TCC floors and things in as we start to push buildings higher, as we need a kind of high level of robustness, high level of performance. The benefits that DCC can bring will be a kind of a strong card to play. So when might you consider using a TCC floor over conventional mass timber or even conventional concrete? If you need a heavyweight screed or finishes on top of your CLT floor for acoustics, why not consider trying to mobilize that structurally and increase performance and reduce materials. If you've got a really large open plan building and large diaphragm loads, again, TCC floors will work really well with those. Sensitive floor uses like laboratories or medical facilities that have a high vibration performance requirement, again, TCC floors will work well. And if you've got a conservative client who likes the idea of timber but maybe isn't quite ready to give up concrete, I think TCC could be a nice gateway drug into mass timber. So in summary, concrete can complement timber in makeup for a lot of those natural deficiencies in performance. So the two materials can work hand in hand. There's plenty of technical information out there for those people that want to explore the options. We're certainly happy to talk to people about the strong floor. And again, try and download those Wood Solutions guides if you want to understand more. I think TCC has a potential to unlock projects that the pure mass timber structures may not be able to touch. It may be that they've got a long span requirement or the height of the building may make it challenging from a fire engineering perspective. So these systems could help to balance these. And we're not here to try and necessarily take market share away from mass timber, but the systems, the ideas can sit alongside each other. So look, we're probably running out of time for questions. So that's the end of my presentation. So thanks for listening.
Thank you very much, Nick. And also to Hamid, thank you so much for sharing your research and development, your background and your knowledge with everyone today. We are a little short on time. I may just bring out one question. There was one question directed at Hamid. For the deflection tests at the university, what timber species and glue was used?
Well, typically we use CLT panels made of European spruce. That's what we used from different manufacturers. If required, I would be more than happy to give you more details as in which manufacturers CLT we have used. In terms of the glues we used for connecting the CLT panel to steel beam, if that's what you're referring to, we use epoxy. And it's an Australian-made epoxy, and we use it quite a lot in different, let's say, structural applications.
Great. There was another question. Great, Hamid. Thank you so much for the presentation.
Yeah, absolutely.
How did you resolve the brittle failure damage in the end? Did you take the element deletion approach or increase the element properties such as stiffness?
For which part? I'm not sure exactly which part of my presentation this is referring to.
Yeah, I do apologize, Hamid.
Yeah, that's okay. No, that's fine.
Came in halfway through.
Yeah.
Now, guys, it looks like we are running out of time to bring up any more questions at this stage. So I will conclude the presentation. Thank you, everybody, for joining us today. And I will let you know that Wood Solutions does run seminars each Tuesday fortnight. But especially with the Christmas break, we will be taking a break. The next one will be on the 18th of January, if everyone can join us, for LCA's Building Techniques. Also, if you've got some time over the Christmas break, please make sure that you check out the Wood Solutions webinar or their YouTube channel. They have some great channels up that show the background on how things are constructed in the manufacturing field. And once again, thank you very much, everybody, for joining us today. I hope you enjoyed and got some great background knowledge into mass timber flooring. I'll see you for the next webinar.